Welcome to Practice number 130, and today we're finishing off this two-part podcast series on surface-piercing propellers. In podcast 129, we went through the theory and the idea of what surface-piercing propellers are. Now we're going to be finishing this off, and we are going to be looking at the second half of this paper called Experimental Evaluation of the Effect of Positioning and Operating Parameters on the Performance of a Surface-Piercing Propeller. Again, this is open access, so you can find it in the link in the description. And let's quickly touch on what we just covered in the last podcast and then move on to what we'll be doing this podcast. So surface piercing propellers are quite interesting because they're propellers, as the name would suggest, they pierce the water, but they don't go entirely inside the water. So for like regular propellers on boats, you put the entire propeller into the water and you just like run it. These ones, part of the propeller is in, so maybe 30%, 50%, or 70% of the propeller is in. And in figure 1, if you're listening to this on Spotify and or Google, you can watch the video on Spotify and or YouTube. And on YouTube, we have other goodies as well that you'll probably enjoy. And with figure 1, we can see what this looks like in terms of the propeller. So the propeller is kind of submerged a little bit in this particular figure. It's 50% submerged. And some benefits of this are that the housing and the axle that connects the propeller to the boat are out of the water. And this means that you can reduce the drag of the entire system because this part, the housing and the axle, are now exposed to air and not water. And air is significantly less draggy compared to water. Now, there's also another reason why you might want to put propellers in this configuration, because this configuration looks quite funky and somewhat stupid to begin with, like, because you think if you put the entire propeller into the water, you have more surface area that you can like push water with. You can lay down a lot more power into the water, whereas in this configuration, half the time or however much of the time the propellers stay out of the water, that's not really producing much thrust. It's only the blades that are inside the water now that are producing thrust. So why would you want to do this? Well, this comes down to a concept called cavitation, which we covered in the last podcast and in other podcasts as well, where if you put a propeller into water and you push it to the certain limits, then you start to get these little pockets of vapor forming on the tips, or it doesn't have to be necessarily on the tips, but on the tips is usually where this occurs. And this vapor doesn't pose a major problem by itself. It's when you look in the bigger picture, which is this vapor, or these little pockets of vapor, which are these little cavities, they're at very low pressure. And this is how they form because you like vaporize the water. It's such low pressure that the water just vaporizes. And then you have all this high pressure around it from the water, the surrounding water. This high pressure then like collapses these bubbles very violently. And these collapsing like phenomena can then result in even shock waves forming in the water. And these shock waves, and even if they aren't shock waves, just this collapsing sends this pressure back into the propeller's blades. And this can then take chunks out of the metal. So that's very bad for the actual operation of the propeller. And okay, it doesn't take, it's not very quick for this to happen. Like it takes maybe 10, 20, 30 years for the propeller to get cavitated to the point where you have to replace it. So the blade gets eroded so much, you have to replace it. Otherwise, it doesn't really work very well. But even still, you're losing efficiency as you do this. So by putting the propeller outside of the water a little bit, what you do is you effectively mix in air into the water. So then this air, which is at lower pressure, it's lower density, it's not going to try to collapse the bubbles in the same fashion that water is doing that. So it allows this vapor to sort of escape into the air and not collapse. So by having, let's say, the propeller 30% into the water, you then put all this air into the water as well, and these bubbles can then like connect to the air pockets and then like escape. And that's how you can get rid of cavitation, or at the very least reduce it a lot. And this is one of the major benefits of surface piercing propellers. The problem with this setup is that you have a very complex multi-phase flow. So you can see these pictures that I'm showing. There's a lot of splash, and not just outside of the water, but inside of the water, there's like, you can see this water, air, vapor mix. So it's a multi-phase flow, which is very complicated, and there's so much going on. So trying to design these propellers and even just understand what they do, like how they do what they do, is quite challenging. And this is what this paper looks into. So in this first podcast that we looked at in podcast number 129, we looked at the effects of the Froude number on thrust coefficient and efficiency and etc. The Froude number is quite an important non-dimensional parameter. And we talked about how not only this concept, but concepts in general can be difficult to test in wind tunnels and water channels when you're trying to scale them. So if you put a boat into a water channel, you have to scale appropriately. You can't just say, okay, I'm just going to reduce the size by a factor of 10. I'll increase the Reynolds number by a factor of, or the velocity by a factor of 10 to match the Reynolds number, because there are other non-dimensional parameters as well that are important to look at, such as the Froude number. And the Froude number, an easy definition of it is the amount of inertia of the flow the amount of inertia of the flow compared to the external field. So in other words, in this particular case, the amount of inertia that the water has compared to gravity. And this is an important parameter when it comes to water in terms of making waves, in terms of cavitation, and in terms of just like operation and how much thrust you're going to be getting out of your thing. The Froude number is very important. Now, the equation for this is quite simple. It's the local flow velocity divided by the square root of the gravity times the characteristic length. Now, the problem with this is, though, even though it is a very simple equation, trying to match similarity with the Reynolds number is difficult, because if you were to reduce the characteristic length by a factor of 5 for the Reynolds number will drop by a factor of 5. The Froude number, though, it will increase by a factor of the square root of 5. So they don't scale at the same rate, and this creates problems. So that's where this similarity condition is quite difficult. And for example, in figures 8 and 9, show the actual images of the propeller at two different Froude numbers. So we have this one here that I'm pointing at to now is the Froude number of 4, and then the one above is the Froude number of 2. You can see they're operating at the exact same kind of conditions, just the Froude numbers are different. And you can see the difference in the splash. It's very noticeable. In addition to what we're looking at with the Froude numbers, we're also looking at something called the advance ratios, where they're looking at advance ratios of 0.3 to 1.2. And in a nutshell, the advance ratio is how fast the tip of the propeller is moving compared to the water. So the advance ratio is the water speed divided by the tip speed. And if this exceeds 1, then obviously the water speed is moving faster than the tip. And this is a factor that does affect the performance of the propeller. You can see in these figures that when we increase the advance ratio, the propeller is splashing a lot more, at least for Froude numbers of 2, or sorry, it's less than at low advance ratios. And then at Froude numbers of 4, then it starts to become a lot more complicated. So the amount of ventilation of the cavitation changes with the Froude number. For example, at the Froude number of 2, decreasing the advance ratio greatly increases the amount of ventilation. And water splash is kind of a good indication of how much ventilation is occurring, how much we are alleviating the cavitation. So like as an engineer, when we would look at this, like let's say we see a boat going along the water and we see a schmuck with his propeller in the water like this, we'd be thinking to ourselves, this guy is reducing the efficiency of his boat because you have all this water splash, which as an engineer, we generally just think like when the flow is not doing what we want it to do, it's inefficient. But the schmuck may actually be very smart, and he is actually trying to alleviate the cavitation on his propeller. Or maybe he might just be a schmuck. We don't know. But either way, there is method to the madness if the madness is the correct kind of madness and not the bad kind of madness. Anyway, let's move on here. So let's cover the rest of this paper here. Let's get into the thrust coefficient. So in figure 10, we see the thrust coefficient in the propeller direction with different Froude numbers. So we have different advance ratios as well on the x-axis, and we go from the Froude number of 2 to a Froude number of 5.5. And the ventilation isn't everything. The thrust is also important because more power is always better. And I know that power is not the same as thrust, but still thrust and power, the more you can get at that, I'm all for that. So the thrust coefficient is a non-dimensional number telling us how good the object is at producing thrust. Anyway, how does the thrust coefficient change with changing at Froude numbers and advance ratios? Fortunately, the thrust coefficient is pretty much independent of the Froude number. So while the ventilation was not, we can see here when we change the Froude number by a factor of almost 3, the thrust coefficient stays almost the same. However, while the thrust coefficient is not dependent on the Froude number, it is dependent on the advance ratio. It greatly depends on it actually. How quickly the blade is rotating through the water compared to the water around it is greatly affecting this thrust coefficient. So in a nutshell, there is a sweet spot that for this propeller's design, which is specifically designed for this surface piercing action, for an advance ratio of 0.8, this is where we get the greatest thrust coefficient. On either side of this, the propeller becomes less good at producing thrust. Interestingly, the drop-off on each side is almost identical. So with an advance ratio of 0.8, the thrust coefficient is 0.095, which is okay. when we go to an advance ratio of 0.2, which is very low, the thrust coefficient is 0.01, which is quite terrible actually. And when we go to an advance ratio of 1.4, the thrust coefficient is minus 0.01. So they have dropped almost the same amount depending on how much you change the advance ratio. And these drop-offs are fairly linear too. So that's always nice to calculate. So let's briefly cover the effects of the Froude number and advance ratio on the efficiency of the propeller before moving on to the immersion ratio. So the thrust coefficient is not everything again. The ventilation, cavitation, thrust coefficient, torque coefficient, efficiency, these are all important parameters to look at when we're designing propellers, because you can get a lot of thrust, but if it's very inefficient, then obviously using a lot of fuel, and that is not a good idea. On the other hand, if you have a very efficient propeller, but you can only move at like snail pace, it's going to take a lifetime to get just to the port. So we need to sort of balance these things. So the immersion ratio, as I mentioned earlier, as a reminder, is how much the propeller is submerged into the water and how much of it is poking out. For this particular case, the immersion ratio is 0.4, and the propeller is pitched at a 3-degree angle of attack. So it's like put into the water at like just below the like level of the water, and it's like pitched down a little bit at 3 degrees. So from figure 12, we can see that going from a very low advance ratio of 0.3 up to 1, the propeller becomes more and more efficient. However, after it reaches the advance ratio of 1, it starts to become less efficient and it starts to drop off. In other words, if the blade tip is moving as fast as the surrounding water, then we're kind of getting the best efficiency. If it is moving slower, then we get a drop off. If it's moving faster, then we get a drop off as well. So it's kind of like we want to have the propeller moving at the same kind of speed, at least the tip, as the water around it. That's an interesting trend there. And this trend holds with different Froude numbers. So we can see different Froude numbers from 2 to 5.5. And this is interesting because for this propeller, we remember in podcast 129, we covered how the authors said that the Froude number can greatly affect the performance of a propeller and even change trends. But here, for the efficiency of the propeller in this configuration, the same trends in efficiency with changing advance ratios regardless of the Froude number occur. So for this particular case, the Froude number is unimportant effectively. So again, when we are scaling our propeller and testing in water channels, in this particular case, if we're looking at efficiency, we don't really need to worry about the Froude number. We can look at the Reynolds number, keeping that constant, or anything else. So that's, again, something to keep in mind. So the configuration of this propeller, as I mentioned, was submerged only 40% into the water. So it's not even up to the axle connecting the propeller to the boat. We should also remember that having the axle above the water helps reduce the drag of the entire boat, because the axle is only producing drag from the air and not the water. So the Froude number does have a slight impact, but it is only on the magnitude seen. For example, the maximum efficiency of the propeller at a Froude number of 5.5 is about 0.6, so 60%, while the maximum efficiency of the propeller at a Froude number of 2 is almost 0.7, so 70%, but the trends hold constant. As the advance ratio increases, the Froude number has an increasing effect on the efficiency. This is enough. That is enough that the Froude number and the advance ratio effects on the various parameters of the propeller. Sorry, that's enough on this kind of topic. Let's move on to the next topic. We've seen that the Froude number is somewhat independent here. It doesn't really affect the efficiency too much. It's just once you get to certain situations where it does kick in, and it's only by a small amount, the trends stay the same. Let's move on to the immersion ratio and the effect of the immersion ratio on the different parameters of the propeller. So let's look at figure 15, which shows how the immersion ratio affects the thrust coefficient with different advance ratios. There is a global trend where increasing the immersion ratio increases the thrust coefficient. However, like in other figures, there's a sweet spot that corresponds to an advance ratio of about 0.8, where the maximum thrust coefficient is reached for almost all immersion ratios. So if we were to increase the immersion ratio from 30% to 75%, we're getting more thrust. And this makes sense because when we put the propeller into the water, we are putting, like when we put more of the propeller into the water, we have more surface area to like push the flow with. So we're going to get more thrust, but is that necessarily going to increase efficiency and or torque, etc.? We'll cover that in a second. We also can see here that as we reduce the advance ratio past 0.8, so down, we reduce the amount of thrust that we get. As we increase it above 0.8, we reduce the amount of thrust as well. So again, there's a sweet spot here. And if we want to increase the amount of thrust that we can get, we want to stay in advanced ratio of about 0.8 for this propeller. Interestingly, having an immersion ratio of 0.05, which means 75% of the propeller is submerged, produces the greatest amount of thrust. I wonder what would happen if we have an entire immersion, so the entire propeller is immersed by into the water. So thrust isn't everything, as I mentioned. Let's look at the effects of the immersion ratio on the efficiency of the propeller. So figure 17 shows this, and from this we can see a completely different picture whereby an advanced ratio below 0.8, the immersion ratio has almost no effect on the efficiency. We found with the thrust coefficient that regardless of what the advanced ratio is, the immersion ratio does affect the thrust coefficient. But here we can see below like 0.9 for the advanced ratio, the immersion ratio doesn't really have much of an effect on the efficiency. Above that, it does start to affect it. So in this range, from 0.3 advanced ratio to 0.9, the effect of the advanced ratio is on the efficiency is quite linear. So at an advanced ratio of 0.3, the efficiency is only 5%, so not really good. At an advanced ratio of 0.8, the efficiency increases to 47% across most of the immersion ratios. There is one outlier in this trend though, and that is when the immersion ratio is only 0.3, so only 30% of the blade of the propeller is submerged. At this ratio, the efficiency follows a significantly different path to the rest of the immersion ratios. First of all, it doesn't really have a linear region at low advanced ratios. Then all of a sudden it hits a peak efficiency at quite a low advanced ratio before diving again. So the maximum efficiency occurs at about 0.65 for the advanced ratio, whereas for the other immersion ratios of 0.35 to 0.75, the maximum efficiency is occurring at a significantly higher advanced ratio. I know I'm talking a lot of ratios, so if you're sort of struggling to keep up with the advanced ratio compared to the immersion ratio, perhaps revisit this podcast and listen to it again. I'll just repeat here that the immersion ratio is how much the propeller is submerged into the water, with 1 meaning 100%, 0 meaning 0%, and the advanced ratio is how quickly the propeller's tip is moving compared to the water around it. And this can range from 0 up to, I guess you can go to infinity if you really like, if you spin it fast enough. So one reason given for the immersion ratio of 0.3 performing quite differently to the rest of the immersion ratios is that because at this low immersion ratio and low advanced ratios, the ventilation of the propeller can occur more effectively. So if we have a low advanced ratio, it means the propeller isn't moving that fast, and also the propeller is not very far into the water. So the air can get into the cavitation much better and alleviate that cavitation. And that's why we get more efficiency at lower advanced ratios. Whereas for the other propeller configurations where we have the propeller like plunged into the water more and it may be moving faster, it means that you have a greater layer of water and or more water splashing around, which is kind of preventing the air from outside diving in and alleviating the cavitation. So that's one idea as to why we're getting such a difference with these immersion ratios and advanced ratios. So that's how the immersion ratios and advanced ratios affect the thrust coefficient and the efficiency. Let's look at another parameter at the shaft inclination angle. So with these ones that we're just mentioning, the shaft inclination angle was 6 degrees. So the propeller was into the water at an angle of 6 degrees to the horizon. With the different inclination angles from 3 degrees to 9 degrees, we have a few figures here from 20 to 24, which show the effects of changing the inclination angle and changing the advanced ratio on the thrust coefficient, torque coefficient, and efficiency of the propeller. And the immersion ratio is 0.4 in this particular case. So the propeller is only submerged by 40%. For all of these three parameters, the thrust coefficient, the torque coefficient, and the efficiency, the inclination of the prop made a little difference, which I found a little surprising. I would have thought that, so I'll show you actually first here that you can see all these lines sort of match up quite closely. There might be like a 10%, 20% difference in some cases, but considering that the angle of attack is so high, or it just changes so much, I would have thought that there would be a bit of a difference here more than this. So, I mean, the prop is being pitched at significantly different angles from 3 degrees to 9 degrees, yet little effect on the propeller's performance is seen. So, as I mentioned, this is an immersion ratio of 0.4, which may mean that the flow coming off the propeller is kind of a mix of water and air due to cavitation and ventilation, which would make its density in between the water and the air, perhaps dictating that the path of the flow coming off the propeller would travel kind of between the water and the air, maybe. I don't know. This is like one thought that I might have had, because that's the only reason why I can think that you get such a independence of the propeller's torque, thrust, and efficiency to the shaft angle of attack. If you have any other ideas, let me know in the comments below. So we can see with other situations, like you can see here with figure 23, the effects of the immersion ratio and inclination angles on the thrust coefficient. And you can see that most of the time they are quite similar. They show very similar trends. It's only when we get to very extreme cases of the propeller being not submerged very much at all, only 30%, that the inclination angle does deviate significantly, the effects of it deviate significantly from the rest of the ones tested. And again, this is probably due to cavitation, I think, and ventilation, where at this situation where we have the propeller not very much into the water, we can alleviate the cavities much better, and that will change the thrust of the propeller. Let's move on to now the shaft yaw angle. We've talked about when the shaft is at an angle like the pitch, so the propeller is like pitched more into the water or not. But what about when we yaw it from side to side? So like, let's say we put the propeller like pointing to the left side or the right side more, or it's like the starboard or the port side of the boat more. How does that affect the thrust coefficient, torque coefficient, and the efficiency? So in figure 27, we can see that increasing the yaw angle reduced the thrust coefficient of the propeller in the direction of travel is diminished. So in other words, when we pitch the propeller at an angle, when we yaw it to an angle and we measure the thrust in the direction we want to travel, yawing it more reduces the thrust as you'd expect, because you have the jet coming off of the propeller being pushed in a not 100% aligned direction. So some of that force that we are producing goes into the side force and not into like their thrust direction. That's why we get this drop off. But if you look at just the amount of thrust coming off the propeller and don't really care about the direction, just like looking at how much power is really coming off, or thrust, I should say, not power, but still, we can see in figures 28, 29, and 30 that the yaw angle doesn't really make much of a difference. So if we just want to know how much thrust we're producing and torque we're producing from this propeller, we can conclude that the angle that the water is coming into the propeller makes almost no difference, which is quite surprising. I would have thought that it would have changed the flow separation characteristics. However, if you remember, I'll scroll back up to this propeller's design. This propeller is very scooped on its trailing edge, and that means that it's really just scooping the water and not using any airfoil profiles or hydrodynamic profiles to manipulate the water. So that could make it insensitive to the water's oncoming direction. So it means that the angle of attack that it's at compared to the water, like the effective angle of attack, has very little effect, because we are scooping the water and not really using the flow to stay attached over the propeller. What's more, because the flow is not going over the entire propeller, and there's cavitation and ventilation, you can kind of argue that parts of the propeller are not actually in contact with the water. So we effectively get flow separation in some sense of like, we actually have different phases being attached to the propeller's blades, which then means that the traditional way of looking at a propeller is not really that valid here, because we are not worrying about flow separation and stalling. We have this scoop situation, and it's just like raw power going straight into the water. So that is potentially why the shaft yaw angle didn't affect the thrust, torque, or efficiency. So that's the end of this podcast we're coming to. We're going to recap the main findings of this study over both of these podcasts that we covered. Let's go back to an interesting picture first so we can see something cool. Let's look at the splash here, and we'll talk about the conclusions found. So a custom 4-blade propeller was designed for this investigation and tested at different immersion ratios. This type of propeller is called a surface piercing propeller. So not the entire propeller is going into the water, it's only part of it. We found that, or these researchers found, I should say, that increasing the immersion ratio generally increased the thrust and torque of the propeller, and the best values occurred at advanced ratios of around 0.8, regardless of the immersion ratio. So this kind of makes sense because if you put more of the propeller into the water, you can lay more power into the water, into like the oncoming water, because you have more surface area to push the water with. But while we get more thrust and torque with more of the propeller inside the water, the best efficiency occurred when the propeller was only sunk into the water about 40%. And this is likely due to the ventilation occurring with the cavitation to alleviate that inefficiency occurring there. So either side of this number of 40% into the water sunk, a lower maximum efficiency occurs, and also the maximum efficiency of the prop was generally seen at fairly high advanced ratios of 1. So we need to move the propeller at about the same speed as the water to get the maximum efficiency. Now onto the Froude number. The Froude number does change the hydrodynamics significantly. However, it's only selectively. When with low Froude numbers, meaning that lower advanced ratios increase the amount of ventilation, which is a good thing. At high Froude numbers, the ventilation appeared somewhat constant with different advanced ratios. And we also found that the Froude number did affect the overall magnitudes, but they didn't affect the trends too much for some situations. So this shows how similarity laws can be difficult to handle. If you were to keep the Froude number constant when scaling, you can ensure that some of the flow physics is preserved, while other aspects aren't affected by changing the Froude number, and other non-dimensional numbers like the Reynolds number might be better to be kept constant. So if you're interested in like the thrust coefficient, then maybe changing the Froude number or keeping it constant with similarity maybe be the better option. You have to look at the actual situation and then make a judgment call from there. And because of this two-phase flow, the flow physics is one of the most complicated you can come across, especially with so much splashing. So this paper was a good one. I liked it. The work is quite challenging, but it helps us understand what is going on in such a complex situation. And mixing in the similarity laws was a good addition to this. So that's in this podcast. And if you liked it, make sure to like. And if you want to get more like this, make sure to subscribe. And if you want to get better at theory and or CFD, so in this we went through theory, but if you want to look at CFD as well, you can check out our course in the link in the description. And you can also check out our other videos on YouTube going through theory on aerodynamics fundamentals. And if you want to make your experiments 2 to 4% more accurate, check out the MSU Hawk. It's an instrument we make which accurately measures the density of air. The reason why this is important is because the density of air changes every day and from hour to hour. So for example, actually just today, where I am, it was sunny in the morning, and then when I got to work, it started to rain and it got stormy, and now it's the afternoon and it's sunny again. And the density of air, I've looked at my MSU Hawk on my desk, and it's changed by about 3 or 4% just in this time. And this is quite normal. Like even if it didn't go from sunny to rainy and just sunny all day, you do get changes in the density of air by 2 to 4%. And this means if I were to go to the wind tunnel, if you were to go to the wind tunnel as well, and test on different hours or different days or months, seasons, you will get very different results because the density of air is different. And going from season to season, you can get density of airs changing by 10 or 15%. And if you don't factor that in, the trends that you find are kind of invalid, because most trends that we do find these days are only on the few percent range. So having a 10% error in the Reynolds number or in the density of air mitigates that, and like it just cancels it out, so you can't even find it. It's lost in error. So the MSU Hawk gets rid of the error for you, and it also helps validate your CFD, because your CFD, when you do it, is based on a certain density. You might specify 1.2 kilograms per meter cubed or 1.225, the two standards, but the density of air is almost never that. It is usually 1.18, 1.19, 1.21, whatever. It is almost never these two values of 1.2, 1.225. So if you run your CFD with these values, and then you get your experimental data and you try to validate your CFD, well, the experimental data that you took was at a different density. So you can't really expect them to line up. And that means that your validation process is more difficult and erroneous. So getting the MSU Hawk gets rid of those errors for you. And you can find that instrument in the link in the description. And I'll see you next podcast. Peace out, amigos.